Have you ever wondered why certain square roots are left in their root form instead of being simplified to a decimal? Well, the reason is because it helps to give the exact representation of that number. It helps you to keep that number in its pure form. Take for instance, you have the square root of 2. The square root of 2 equals 1.414. It goes on like that with it's unending with non-repeating numbers. Let's say you're trying to use two decimal places for this problem. Then you are dealing with 1.41. By using 1.41, you are foregoing the other numbers that you have right behind this. And the implication of that is the number you're working with is going to lose some of its values. Now, we are not trying to make it lose some of its values. We are trying to keep your sword in the pure form, in its pure state. And that's why we're looking at the topic before us, which is sword. Hello, and welcome back to Simpler Math. And in today's video, we're going to delve into the concept of sword. If you are new to this channel, endeavor to subscribe and like this video. Thanks. Now, I'm going to introduce sword to you as a number, which of course it is. And we're going to categorize this number into two, right? Not all numbers are sword, but all sword are number, right? So we're going to look at them as rational and the irrational. Now, rational numbers are numbers that can be expressed as a ratio of two integers. That is, if you can write it as p over q, then it is rational, provided that q is not equal to 0. For instance, you can have 2/3, 3/4, 1/2, etc. Don't forget that you should always take note that q must not be equal to 0 because you cannot use 0 to divide any number, else it is going to be undefined. Now, this category includes fraction, integers, and decimals. Not all decimals in this case, some decimals. And these are the decimals that can be converted to fractions, right? So we can refer to these decimals as rational, e.g., 1.1. This is going to give you 11 over 10, and 1.333 repeating, which can be shortened as 1.3 with a vinculum. This is equal to 4 over 3. So these are rational numbers. Now for the irrational part, for the sake of what we are learning, I'm going to group them into derived constants, and non-perfect roots. Non-perfect roots. Now, derived constant includes the Euler number, pi, the golden ratio, which is 1 plus root 5 over 2, which you find it being represented as phi. Now, the non-perfect root is where sword belongs. What are non-perfect roots? First, we have to understand that there are these numbers called perfect squares, perfect cubes, right? Perfect quartics, basically, perfect quintics and all that. So perfect square are numbers that when you take their square root, square root, right? When you take the square root, you have rational numbers. Perfect cube, when you take the cube root, you have rational numbers. Perfect, like that. It goes on like that. Now, example of perfect square include 9. Okay, let's start from the beginning. 1, 4, 9, 16, 25, etc. So when you take the square root of each of these numbers, you're going to be having exact values like 1, 2 for this, 3 for this, square root of 16, 4, square root of 25, 5. Now, it can also be in form of fraction. It could be 4 over 9. When you take that, you have 2/3. When you have the square root of 9 over 16, you have 3/4. Same thing goes with cubes. Uh, Perfect cubes include 1, 8, 27, 64, etc. So when you take the cube root of each of these, cube root of 1, cube root of 8, cube root of all of this, then for the cube root of 1, you have 1, 2 for 8, and 3 for 27, as well as 4 for 64. Now, what are we trying to point out? Any number that does not belong into any of these categories that we've mentioned, take for instance for perfect square 1, 4, 9, 16, any number that doesn't belong here between 1 and 16, and then you're trying to find the root, is a surd. That is the square root of 2, square root of 3, the square root of 5, square root of 6, square root of 7, square root of 8. It goes on like that. These are referred to as surd. Now again, if you have, between 1 and 8, we have 2, we have 3, we have 4, etc. So when you take the cube root of 2, the cube root of 3, cube root of 4, these are numbers that don't have exact values. They're irrational and they are referred to as surd. Now, the square root of 2 is surd, and the cube root of 2 is also surd, based on the reasons that we've mentioned earlier. But what differentiates this surd from this surd? We refer to this surd as quadratic surd. Quadratic surd. And we refer to this as cubic surd, or in certain cases you can call it a surd of the third order. This is the second order. There is no first order. Third order. So that's what we're learning. Now we are narrowing our focus on just quadratic surd. Alright, we are keeping the cubic surd for later times. Now, what are the things to note when you are dealing with surd? First is that you cannot have a surd if the number you have under the radical sign is negative. For instance, the square root of -2 is not a surd. A must be greater than or equal to 0. The second point you need to note is that when you have two separate surd, let's say square root of A times the square root of B, both can be combined as A multiplied by B, which is AB. That is, if there is a square root of 2 and there is a square root of 3, both can stay under the same umbrella. 2 times 3, this equals to the square root of 6. Another thing that could possibly happen is if you have the square root of A over B. You can split this up as the square root of A over the square root of B. Or let's say you have the square root of A over the square root of B. You can write it as the square root of A over B. So it doesn't really change anything. It's the same. But for all of these cases, A must be greater than or equal to 0, and B must be greater than or equal to 0. Now, if you are dealing with addition or subtraction, caution has to be exercised. Take for instance, you are trying to add the root of a and the root of b together. If the values of a and b are not the same, then you shouldn't add them. Obviously, the mistake anyone would have made here should be equals to the square root of 3 plus 2. And this is not true. You shouldn't add. But if they are of the same form, you can add. Like for instance, you're trying to add 2 root 3's together. We can see that this is 1 and this is 2. So we have 2 of them that can be added. So this is 2 root of 3's. Also, when you're trying to subtract, it follows the same process. Square root of 3 minus the square root of 2 is also not obtainable this way. But if you have sort of the same form, let's say 3, the square root of 3 minus 2, then the square root of 3. Then we have 3 of this, 3 of the square root of 3, and 2 of them here. So it's like 3 minus 2, you have 1. So this is equal to just 1 square root of 3. Now, sort are of two types. We have the non-basic, and then we have the basic. Now, the non-basic are the ones that have perfect square as a divisor, while the basic are the ones that do not have. E.g., the square root of 8, for instance, has a perfect square, which happens to be a factor. So we can split 8 as 2 times 4. Now, 4 is a perfect square, alright, which makes the square root of 8 non-basic. Now, we can look at another example. The square root of 32. This can be written as the square root of 16 times the square root of 2. This square root of 16 itself is rational. 16 is a perfect square. That will make the square root of 32 non-basic. On the basic side, we can have 7. There's no way you can split 7 up. The only thing you can do about 7 is the square root of 1 times the square root of 7, 7 being the prime number. Though you can argue that the square root of 1 is basically 1 is a perfect square, but we are not considering 1 in this case. So the perfect square we are saying by definition is an exclusion of 1. So which means we can still refer to this as a basic surd. One last example. If you have the square root of 6, the square root of 6 is the square root of 2 multiplied by the square root of 3. This is also basic form. So what we are doing is, if we have a non-basic surd, how do we take it to basic surd? You may be required to express as a single surd. A single surd is a surd that is written in such a way that everything that has to be written about that number is under the square root sign. For example, the square root of 18 is a single surd, while 3 square root of 2 cannot be regarded as a single surd. So now, how do we change the 3 square root of 2 back to square root of 18? All you have to do is to take a look at each of the numbers that makes up the whole 3 root 2 itself. So 3 times root 2. Of course, this is already in the root form, so we are leaving that. Then we are focusing our attention on just the 3. 3 is a result of taking the square root of a number, and that number is 9. So when you take the square root of 9, you have 3. So multiply by the square root of 2. This equals to the square root of 18 when you take 9 and 2 together. Also, if you have to take root 3 and root 2 as a single surd, then you just have to take the product. You have 3 multiplied by 2. Now we are taking the 3 and the 2 under the same radical sign. 3 times 2, 6. Lastly, let's say you had to simplify the square root of this raised to the power of 2. Now this means the 3 root 5 times 3 root 5 in two places. We can take a case where we'll have to multiply the 3 and the 3 together to give 9. And then when we take the root 5 and the root 5, you have 5. So the answer to this equals 45. Again, we can say that two surds multiplied each other to give a rational number.